and welcome back to CS103 Machines, Languages and Computation. To finish this week, we're going to look at a rather ingenious proof due to Euclid that there are an infinite number of prime numbers. And this proof by Euclid uses a method called proof by contradiction. We're going to be using proof by contradiction later on in the module to prove that there are such things as non-computable functions. So let's have a look at it. So there's three types of proof that I want you to know about in this module. There are others, but these are the ones we're going to encounter. The one that you've already seen is called direct proof. That's the if P then Q style of proof. You start with some axioms and some definitions and earlier theorems, and then you make logical deductions in a kind of forwards thinking way from those things, and you proceed towards the goal that you're trying to prove. The second one is proof by contradiction. That's what we do here is we take the statement that we want to prove and we assume the opposite. We assume that the statement is false and we see where that leads us to. If we get to a logical contradiction, like 1 equals 2 or something like that, then we know that the statement must be true, because proving things from a false statement will lead to a logical contradiction. Finally, proof by induction is a special method that we can use when we've got the natural numbers. If we're trying to prove something over the natural numbers, that's the counting numbers, then we can do it by knowing that there is a first case and that there is always a successor to the number. So the first case, successor to the first case. I'm not going to say anything more about it here. What I am going to do is I'm going to look at proof by contradiction. And we're going to do a proof by contradiction on prime numbers. So let me remind you what prime numbers are. So this is the definition that you may know of prime numbers. It's not quite right, because the number 1 is not prime. So you might think if a prime number is any integer greater than 1 that divides exactly by only itself and 1, well, 1 fits the bill. Well, it does indeed, but that's not what a prime number is. Euclid told us, he was a clever chap, that every positive integer greater than 1 can be written uniquely as the product of prime numbers. So prime numbers are really these kind of building blocks that you can make other numbers out of. So for example, if we take the number 12, the building blocks of 12 are 2, 2 and 3. That's the unique way of expressing 12. You multiply 2, 2 and 3 together, then you get 12. And the prime numbers are the building blocks that you need in order to make this happen. So all of the positive integers greater than 1 are either prime or they are composite. All of the composite numbers can be written in the form a times b. So those numbers which can be written like that are called composite, as I've just said, and all integers are either prime or composite. So let's have a look at the numbers. Here's the numbers, the counting numbers from 1 to 100. Let's see which of these are prime numbers and which are composite. Well, I've told you already 1 is not prime. It can't be, because it would break that theorem that I told you about. So we remove it and it's gone. 2 is a prime number, but all of the multiples of 2 must therefore be composite. So 4, 6, 8, 10, all of the even numbers are composite. They're 2 times something. So we get rid of them. So we're just leaving the prime numbers behind. 3 is prime, but all of the multiples of 3 are composite. So here they all are. 9, 15, 21. We've already removed 6 and we've already removed 12, so that's why they haven't lit up. But all of these numbers here are composite, so therefore we remove them. 5 is a prime number, but all of the multiples of 5, and here they are in a nice column rather, all of the multiples of 5 are composite, so they go as well. 7 is prime, but its multiples are composite, so we get rid of them. 11 is prime, and the first multiple of 11 that we would look at is 121, so it's not in this table. So these numbers that remain here are all prime numbers. So this is the sequence of prime numbers: 2, 3, 5, 7, 11, 13, and so on. What you'll notice is that there's quite a few of them to start with. So there's 4 in this row, 4 here, then only 2, 3, 2, 2, 3, 2, and only 1 in this row. 97 is the only prime number in this row here. So they're thinning out as we go along. So I wonder if they thin out altogether eventually. That's what Euclid wondered. I wonder if they do thin out all together or eventually, or I wonder if they do actually go on forever. So Euclid did this proof by contradiction. So he wanted to show that there were infinitely many prime numbers. Assume the opposite of that. Assume that there are a finite number of prime numbers, and that means there must be a biggest prime number. Okay, let's assume that there's a biggest prime number, and we're going to call this prime number n. So after n, no more prime numbers, just composite numbers all the way up to infinity. Okay, so the first thing that Euclid did was that he said, well, let's form the factorial of that number n. And at this point you're going, whoa, why has he done that? Why has he done that? And the answer is, it's because it helps with the proof. He could have done a lot of things. He could have said, let k equal n squared. Let k equal n to the power n. Let k equal n plus 37. He could have done lots of different things, but none of those would have helped very much. But forming this number k, which is the factorial of n, that helps with the proof. So that's why he did it. So there's many different, this is how proof works. There are many different things that you can do. You try some, and then once you find the sequence that gets you to the goal, then you write down that sequence. And then it all looks very clever. When we come on to the MIU system, of which I'll say more in a minute, you'll realize that you can go down the wrong path in a proof, and then you don't end up anywhere. But once you do find the proof, then you can just write a nice path to it. So this is the first step in Euclid's path to his proof. I'm sure he tried lots of paths that didn't lead anywhere as well, unless he was very lucky. So he's formed this number k. It's the factorial of n. Remember, n is the biggest prime number, so the factorial of that's going to be quite a big number. Is k prime? Well, no, it's not. It divides, well, it divides exactly by every integer up to n. So it's really composite. It divides by every number that there is. It divides by 2, it divides by 3, it divides by 4, 5, 6, all the way up to n. What Euclid did now, though, was that he took this number, this big factorial, and he added 1 to it to form a number m. Again, this is just the step that he needed to make his proof work. And then he considered dividing this number m by every number up to and including n itself. So let's take k plus 1, which is the factorial of n plus 1, and let's try dividing it by 2. It isn't a multiple of 2 because it's going to leave 1 over. In fact, you can see that k, being a multiple of 2, k must be an even number. Therefore, k plus 1 must be an odd number. It will therefore leave a remainder of 1. So in other words, m over 2 is going to be something, remainder 1. So let's try dividing it by 3 now. Well, k itself divides exactly pardon me, by 3, but k plus 1 therefore will leave a remainder of 1. And if we try dividing it by 4, again a remainder of 1. By 5, a remainder of 1. By 6, a remainder of 1. So it doesn't divide by any number up to and including n itself. So this k plus 1 thing, well, it doesn't divide by any of these numbers. So that is k plus 1 a prime number? Well, it might be, or it might have a prime divisor, but that's guaranteed to be greater than n because we've already tried all the numbers up to n. So the first number that k properly divides by is going to be a number bigger than n. But that number, the number that divides by, it's got to be prime. If it's not prime, then, well, we would have divided by it earlier. Now that's a hard old proof, that is. What I'd suggest that you do in order to try to get to grips with it is try an actual value for n. Try it for, say, n is equal to 5, say. Form the factorial of 5. Well, I can tell you, that's 120. Then add 1 to it, 121. Now try dividing it by every number from 2 upwards. 2, 3, 4, 5. Doesn't divide by any of those. And in fact, the first number that it divides by is 11, which is prime. So in other words, we assumed that the biggest prime number was 5, and we then showed that there must be a bigger prime number, which in this case is 11, and that works for any value. Try it for n is equal to 7 and see where you get to. Try it for different numbers. If you're already a programmer, you might even want to write a program to do this for you. And that basically you input the biggest prime number, and it will then tell you, by following this procedure through, what a bigger prime number is. So in other words, what this proof does is it's a kind of algorithm. You feed into it the biggest prime number, and it tells you, guaranteed, a bigger prime number. So therefore there cannot be a biggest prime number, because this procedure, whatever that so-called biggest prime number is, this procedure will give you a bigger one. And that's the end of the proof. So we'll be looking at that proof again because it's worth looking at. It's an interesting proof. Next week on the class, I'm going to show you proof by induction. Proof by induction is something that works on the natural numbers, and I'm going to show you why everyone in an infinite halls of residence will get a carry. Then we're going to look at the MIU system. The MIU system is a really good way of thinking about proof. We're only using symbols and rules, and they won't mean anything to you. So it's not like doing proofs in maths, and we're going to try to prove MU. And then finally, we're going to start looking at decision procedures, and these are very important things. These are algorithms for deciding if an input is a thing or is not a thing. So an example decision procedure is, in fact my daughter's just written this as an example program at her school, you feed in a number and it decides whether or not it's prime or not. So that's a decidable problem. How many problems can we think of that are decidable, and are there any problems that are not decidable? See you next week.